Somebody want to join? Sorry, let me join quickly. So let's begin the fourth part quickly, and this is now predicting diabetes with logistic regression. Logistic regression is a very useful and highly preferred technique in data mining and machine learning. It's quite easy to understand and easy to use. It uses what we call the logistic function or the sigmoid function to transform the input variables to give you a probability of your outcome being yes or no. So normally it works on binary outcome, either yes or no, 1 or 0, positive or negative, and so on and so forth. You can read more about it. Again, this is worth its own session to explain how it works and why it's useful. But let's fit it quickly to our data. So we're dealing with the glucose, BMI, and age, and our outcome is either 1 or 0. Let me split the data now so I can take these variables now to be my input and this column to be my output. That's what I do here in this line. To X is my data and Y is this column here. What I do here is, so typical machine learning, I split the data into train and test data. I have a very small percentage for testing, just for quick performance. I fit the logistic regression model, and now I try to estimate its performance. Okay, it's giving about 83% accuracy. That's good, not bad, but that's not what we're interested in. We're interested in now using this model to predict the same test point we had here, the same point, this point here. So after we've trained the model on the same on the data now, what I can do here is I can look at the contribution of the variables, and this is quite interesting. So we have 3 variables: BMI, age, and glucose, and this bar here shows me how much contribution BMI is making and how much contribution age is making to the model. Basically, what this means is logistic regression thinks that BMI is the most crucial factor when it comes to predicting diabetes. This is according to this data set we're using now. The second most important factor is the age. The third most important factor is the glucose. Now, this might be counterintuitive. If we go back to the correlation matrix, you'll see that glucose has a higher correlation with the outcome probably than BMI. So why is it the case that BMI now seems to be more important? That's what this model thinks, and probably because some other data in the correlation is not captured or maybe scattered between different variables. Okay, so this needs some medical background to be able to interpret this quickly. But our model is saying BMI is more important than the other two. And to look at these features, for glucose, the importance is 0.03. It's the number are quite low because of the way the regression works. It transforms things in between 0 and 1 using the logistic function and so on and so forth. That's why the values are low. Okay, they're quite close to 0. And it's saying it's the impact is positive. So none of them is having a negative impact, meaning when that value increases, the things go into opposite direction. Okay, so I've done that here as a quick summary that BMI level has the most significant influence of the model than glucose. Does it make sense? Any medical experts with us here today? The second highest influencer is age. The third highest is the glucose level. Well, like I said, it doesn't seem to be sensible, but that's what the model is saying. The 3 of them have a positive influence on the prediction, i.e. their higher values are correlated with the person being diabetes, so it goes into the opposite direction. The correlation tells us that glucose is more correlated than BMI to the outcome. I said this, that glucose is more correlated to the outcome than the BMI. But the model relies more on the BMI. Does that make sense? This can happen for several reasons. Maybe the correlation captured by glucose is captured by some other variables, perhaps. This is worth investigating further. But now the important point, well, let's have another look at the correlation. You see the glucose is highly correlated with the outcome, higher than the BMI and the age. But now, after creating this logistic regression model, can we predict the probabilities of that test point being diabetic or not? This green point here is the same value. Let's have a look and see if the 2 models agree, the statistical model and logistic regression. So let's do it. This is my test point, the same values, 110 for glucose, 35 for BMI, 52 for the age. If I make the prediction whether 0 or 1, it tells me, okay, the value is 0, but I want to say, give me the probabilities. And if I take the probabilities now of the point belonging to class 1, i.e. 0 or class class 0 or class 1, it tells me that, okay, I think there's a 54% chance, that's the probability, 0.54, of it being negative, and 45% chance of it being positive. And that's really interesting because the two models agree, as you can see. So my logistic regression model and this probabilistic model, both of them agree that there's a less chance of this point belonging to a diabetic person. Okay, the values or the probabilities are slightly different, but the outcome is the same, that there's a slightly lesser chance of it being diabetic and a slightly higher chance of it being non-diabetic. And that's quite interesting. I remember when I trained the logistic regression model, I didn't use the whole data. I took one part of it to be my test. So I split the data into train and test part. If I train the model on the entire data set, probably the values of these probabilities will change a little bit. Okay, this will go down a bit, this will go high a bit. It'll be much closer to the actual probabilistic model. Having said this, so like I said, the two models agree, which is great. That's a really good outcome of this tutorial. Having said this, I'd like to say well done. Thank you very much for joining us. And that's the end of my talk. Let's see if we have any questions. So for the Q&A, I prefer the chat, but if anyone wants to use the mic, then it's fine. So let me see if we have any questions. You can make screen more smaller so that more information will be shown. Sorry, I wasn't looking at the chat. What's the BDF stands for? Somebody answering this probability density function. Yes, so it's an approximation of the probabilities of your data. This is highly useful when you want to model your data, maybe for example, and make predictions. For example, predict how probable some value is, or sometimes how probable a value is between the range of two values, or you want to draw data from the same distribution, make or create a similar data set. Modeling here is very important. Okay, any questions? Yeah, for the discrete outcome, it's PMF, at a mass function. Thank you, Adel, for saying that. Okay, any questions? Please, can we have the Jupyter Notebook code as part of the souvenir? Okay, thank you. Somebody wants the code. Okay, I'll put the code on GitHub. You have my email. If you email me back, I'll send the code to you, okay? I'll send you the code. What is the minimum number of observations that's needed for an ANN technique? Okay, somebody's asking about neural networks. Neural networks are known to be data hungry, and I don't have an answer for, what's the lowest number of observations. The more data you have, usually the better. So there's no magic answer to this. Okay, Malik is asking about, it's a different area, neural networks. Maybe one day we can have another session on them. But Malik is saying, how many instances do we need normally? I don't have a magic answer, to be honest. There's no really one specific answer. The more data you have, usually the better. Okay. Okay, any other questions? Okay, I guess I can stop screen sharing now.
I have one, sorry.
Okay, somebody's speaking. Okay, go ahead, please.
Yeah, thank you very much for this wonderful presentation.
Thank you.
It was really nice to know more about how these things work. And I was the one that asked if you could kindly send the Jupyter Notebook to us. It will be very grateful to practice. But for my question, can you hear me, please?
Yes, I can.
Yeah, when you started, there were none, and you said that we should remove that. What if the column that we are trying to remove happens to be the most important column that correlates to the outcome that we want to predict in this case? Will it not be a fatal accident or fatal mistake to have removed the column prior to knowing the correlation between the outcome and the specific column that we want to remove?
Brilliant. Okay, thank you very much for asking this question. Really interesting. Okay, point number one, if you have my personal email, if you email me back, I'll send you the Jupyter Notebook. Okay, that's number one. Number two, like I said, dealing with the missing values now is up to you. So I've removed insulin because nearly half of it is missing. But if you want to keep it and then remove the rows that have missing values, you will see that your data, instead of being 500 and something rows, will be probably in the 300 something. So you lose a lot of data. That means your modeling now will be less accurate. Okay, this is up to you now. If the most crucial column in your data has a large number of missing values, your data is problematic, and you need to look at ways of collecting more data. Yeah, or you'll have to work with the small data size that you have. This is up to you. Okay, it depends on the situation, the type of data you're dealing with, and always remember. In the beginning, I said these techniques. This is up to you. I just here to show you how they work, what they mean, and why they're useful. And then it depends on the situation you're solving, the problem you're solving, you're addressing. What are you trying to answer? Okay, excellent question. Thanks for asking it.
Sorry, my last question, please.
Yes. Okay, go on, please.
Yeah, yeah. You talked about data imbalance in one of I mean for the outcome value
Yeah.
now.
Yeah.
But from what I observe, I think this data is quite balanced because there is not too much of imbalance in the data set. But I mean, because this is like a 50 to 40 something percent. But I mean, you know better. But my question basically is, what of in the future if we really have a case of a very severe imbalance in the data set? For example, where the number of diabetic patients is 70% and the non-diabetic is 30% in this case, is there a way to undo the imbalance in this case?
Nice. Okay, super. So I actually teach techniques on how to deal with data imbalance, and that's a very long tutorial. That's a long lesson. Yeah, it can take several hours. But in general, this data set can be seen as imbalanced because the number of non-diabetic persons is almost twice. So it's 2/3 are healthy, 1/3 are non-healthy, are diabetic. So you said 70/30. This data set is probably 60/40 or 65/35, so close to what you said. So it's still imbalanced. But when you have severe imbalance, then you need to always pay attention to the fact that probabilities need to be calibrated and weighted, or you can, for example, undersample the majority class. So you can remove examples from the majority class so the data is balanced. So that's another technique, okay? Or for example, if you do machine learning and you want to focus on the accuracy is not always useful when you have severe imbalance. There are other metrics that consider the imbalance or use the number of instances in different classes in calculating the evaluation metric, so you can use them. Okay, so accuracy is not always great. Okay, hope that answers your question. Let me see if you have a question in the chat. Thank you. Okay, thank you all. So, but to choose the best test based on normality in case the first variable normal distributed, the second is not. So what I said before is that we can actually do some transformations on our variables, and that's a different topic, to make them normally distributed. But remember, our data is not actually big. That's why I use the PDF function that assumes normality, and I did the modeling because the data is quite small. So when you have large data set, excuse me, things seem to be better behaved, okay? So based on what you did in logistic regression, can be other techniques by use. Okay, you can experiment with other techniques if you want to make predictions. You can use other techniques that give you probabilities of your outcome. It's fine. So you can use, for example, naive Bayes. Abdullah, naive Bayes is good. Is a good one. Somebody says thank you all. Somebody says, what is the best way for dealing with missing values such as BMI? Yeah, so the best way depends on the area. So let me give you this, for example. If you have a column that's 95% available and only 5% of the data is missing, so that's a really small fraction of the data is missing, then instead of dropping it, you might want to say, I want to replace the missing values with the mean or the median of that column. But if your column has a large percentage of missing values, then it's difficult to use the mean. Okay, especially if 40%, 50% is missing, the mean or median are not a good indicative of the other data values, and that will change the results of your modeling. So if you want my experience, drop it, try to collect more data. Unfortunately, it's not, there's no magic answer to this. What is the perfect prediction model for daytime data like monitoring real-time supermarket, Adel is asking about time series analysis. You can experiment with the models from the ARIMA family, ARIMA, ARIMA. So it's based on moving average and stuff like that. Or you can use um, neural network. So for deep learning, there's a class of neural networks called uh, LSTMs, so long short-term memory, or GRUs, gated recurrent units, or RNNs, recurrent neural networks, or even CNN, convolutional neural networks, also useful. So these are different techniques for dealing with time series data. Great presentation. Thank you very much for saying that. The recording will be available, so I'll send it to you later on or tomorrow. Thank you, Abdullah. Thank you, Usama. Abdul Ghani Yahya, thank you very much. Okay, so any more questions? Somebody wants to join now? We just finished. Probably they got the time wrong. Yeah, they got the time wrong, I think. Okay, so for those who joined now, we've just finished the presentation. Any questions? Okay, if there are no questions, then I'd like to thank you very much for attending. Remember, you will receive the link to the YouTube tutorial, the YouTube video. I'll probably split it into smaller parts, so it's easier to watch maybe later on. You have my email. If you have any queries, please feel free to contact me. And if you don't mind, I'll email you future announcements. If you don't want to receive future announcements, please email me back and say you don't want, and I'll remove your list from, I'll remove your name from the email list. Otherwise, you'll receive future announcements. If you're interested, then please remember to invite friends. We always share knowledge. Somebody says, greeting from Algeria. Saif, oh, Saifullah is my friend. Thank you, Saif, for joining. I miss you. Thank you. Okay, so I'm going to end here. Those who joined us now, unfortunately, we've just finished.